The research program at Younès Messaddeq laboratory is focused on the development of a new generation of materials for optics and photonics, such as new optical glasses, glass ceramics, and optical fibers based on heavy oxide, phosphate, telluride, and chalcogenide glasses. For years, Younès Messaddeq laboratory has been tailoring materials to provide unique emission spectra, nonlinearity, magneto, electro-optical, or thermomechanical properties. More recently, the group has concentrated efforts on elaborating new glasses with a wide transparency window in the mid-infrared region for a new generation of optical fibers and amplifiers. Professor Messaddeq's laboratories are located at the Center for Optics, Photonics and Laser, the COPL, at the Université Laval in Quebec City, Canada. The center has 107 laboratories and 5,000 square meters of Class 5 clean room. The temperature is controlled in each laboratory all year long. The most sensible laboratories are located underground to minimize mechanical vibrations. In addition to state-of-the-art equipment for optical fiber manufacturing and preform fabrication, the laboratories are equipped with sophisticated optical testing and measurement instruments. In this video, we will guide you through Professor Messaddeq's laboratories at the COPL's facility, starting with the glass preparation laboratory, followed by the preform fabrication laboratory and fiber drawing tower. Finally, we will show you some laboratories dedicated to the characterization of materials. In the oxide glass laboratory, heavy oxide, phosphate, and telluride glasses are prepared by melting high-purity precursors and then quenched in molds according to the application. The variety of furnaces allows the melting of glasses ranging from a few hundred to 1800 degrees Celsius. A glove box equipped with multiple furnaces is used in applications requiring a refined control of the atmosphere, such as glass compositions where the purity is critical and precursors that are sensitive to environmental humidity. Chalcogenide glasses are known for their transparency in the infrared region, up to 20 micrometers. Professor Messaddeq's laboratory is the unique research facility in Canada able to produce high-purity chalcogenide glasses and optical fibers. Everything starts with the ampoule fabrication, which is made by our research personnel for each specific purpose. The precursors are distilled, redistilled, and stored in a dedicated glove box. When a researcher or a customer needs a glass composition, these precursors are weighted and a purification setup is assembled. The glasses are melted in a rocking furnace for several hours to guarantee their homogeneity. Each glass composition can be distilled up to 3 times to ensure its purity and transmission in the infrared region before being drawn into a fiber. At the frontiers of materials innovation, new organic glasses and hybrid materials are developed in the Sogel laboratory for functional coatings, which can be applied by a deep coating machine developed by our team. These materials can also be 3D printed using a multi-wavelength stereolithography printer developed by our PhD researchers and technical staff. In the modified chemical vapor deposition process, also known as MCVD, precursors with ultra-high purity are deposited in the inner part of an equally high-purity silica tube to build a preform which will be drawn into an optical fiber. The volatile precursors will form the core of the fiber, whereas the tube will form the fiber cladding. A controlled mix of volatile precursors of aluminum, phosphor, silicon, and germanium allows the precise control of the optical properties of the fiber. As the mixture is heated, it forms a deposit known as soot. The tube containing the soot is thermally treated to convert the porous soot into a glass layer. This step is followed by the tube collapse. The preform is almost ready. After cutting, the preform can be drawn into a fiber. Professor Messaddeq's laboratory has the know-how for drawing any kind of optical fiber, from mid-infrared fibers such as telluride, galates, and chalcogenides, to polymeric and microstructured fibers, as photonic crystals and multi-core fibers, as well as the more common silica fibers. 2 fibering towers are installed in a laboratory dedicated to the research in fiber drawing. An 11 meters tower is dedicated to silica fibers with a graphite furnace able to reach 2200 degrees Celsius. Here, we observe the first drop flowing at the beginning of the drawing. The filament that comes just after it will form the optical fiber. The fiber diameter is closely monitored along the process and controlled by optimizing the temperature and drawing speed. A double polymeric coating is applied to protect the fiber, improving its mechanical resistance. On the second tower, non-silica glasses, also known as exotic glasses, can be drawn into fibers. We have a set of 4 furnaces at hand to choose the best drawing conditions. For example, a double crucible furnace is frequently used for chalcogenide fibers, where molten core and cladding glasses are inserted one into another just before drawing. For compositions prone to crystallization or chemically sensitive, a furnace with a controlled atmosphere is put in place. The thin film deposition is performed in a hybrid evaporation system, containing an electron beam and a thermal evaporation source. Therefore, glass compositions otherwise difficult to obtain can be formed by co-evaporating materials. The wide chamber fits not only usual substrates such as glass slides and silicon wafers, but can also be used for substrates up to 60 cm wide, like mirrors and even preforms. Our research group counts on a variety of laboratories for characterization and material analysis focused on the optical, mechanical, magneto- and electro-optical properties of crystalline and amorphous materials. The laboratories are equipped with a range of instruments for the characterization of advanced materials of high and low dimensionality. Optical fibers and bulk glasses are characterized using a different set of equipment and techniques. We use an ultraviolet visible near-infrared spectrometer to measure the light absorption in bulk samples and thin films. Vibrational spectroscopy is performed in a Raman confocal microscope equipped with multiple laser sources and able to map samples at a submicrometric scale. Our group also possesses a high-resolution prism coupler for measuring refractive indexes. An accessory can also be used to couple the light in thin films and measure its refractive index and thickness. We assembled a spectrofluorometric platform for steady-state and time-resolved fluorescence measurements up to 4.5 microns at room and cryogenic temperatures. A large set of accessories allows the measurement of optical fibers, microscopic, liquid, and bulk samples. Our laboratories are equipped with a variety of optical microscopes and with a scanning electron microscope that permits the microstructural characterization of the materials with high-quality images. With decades on expertise in optical materials, our group has been actively collaborating with industrial partners and research teams around the globe. Beyond the optical research, our team is also working on other frontiers of science, like smart textiles for healthcare applications, wastewater treatment, optogenetics, and a new generation of semiconductor devices.